So continuing the topic of complex numbers, we will now take a look at something known as the complex plane. Now, if I were to consider a Cartesian plane where we have an x and y axis, we can easily identify the location of a point on my Cartesian plane using an ordered pair like this, where x and y are real numbers. Right? Now, similar to this, we can also represent geometrically complex numbers that are of this form, x plus iy, on something known as the complex plane. Right? Onto something known as the complex plane. We can also refer to this as an Argand plane. Right? So similar to the Cartesian plane, the complex plane also has two axes. The horizontal axis is my real axis, and the vertical is my imaginary axis. Right? And similar to how we can plot the coordinates xy on a Cartesian plane, we can also plot the complex number x plus iy on my complex plane. So let's consider, for example, we have 1 plus 2i. Here x is equal to 1 and y is equal to 2. So my real part is 1, my imaginary part is 2. So what I can do is I can consider 1 unit to the right of my origin on my real axis. So this is 1. And then I can go 2 units above. And this will give me 1 plus 2i. This is 2. So this is going to be 1 plus 2i. Similarly, if I were to consider minus 5 minus 3i, then I will go 5 units to the right. This will be minus 5. And then 3 units down. And this will be the point minus 5 minus 3i. Right? So that is how we can plot complex numbers on a complex plane. So now let's consider some complex number, z, and this is equal to 2 plus 3i. Let's try and find the complex conjugate of this. Let's find z bar. Z bar meaning we're finding the complex conjugate of z, and this will be just equal to 2 minus 3i. Similarly, for minus z, we will have minus 2 plus 3i. This will be equal to minus 2 minus 3i. So let's plot all of these complex numbers on a complex plane. This is my real axis, my imaginary. So starting off with z, we have 2 plus 3i. Let's say 2 plus 3i is somewhere here. Right, this is my z. And now let's plot z bar. So we can see that we have the same real part, but opposite imaginary part. So we will have along this same vertical line, we will have z bar, which is equal to 2 minus 3i. And for minus z, we can see that we have the same imaginary parts. So z bar and minus z, they have the same imaginary part, but opposite real parts. So minus z will be along this horizontal line, somewhere here. Let's say this is minus z, which is minus 2 minus 3i. Right? So now we can clearly see that since z and z bar have the same real part but opposite imaginary parts, z and z bar, they are just reflections of each other over my real axis. And similarly for z bar and minus z, they have the same imaginary part but opposite real parts. So they will just have, so these 2 points, z minus z and z bar, are reflections of each other over my imaginary axis. Right? Now, is this the case for all complex numbers? Does this hold true in general? So let's consider z is equal to a plus bi, some arbitrary complex number. Then let's consider z bar. This is a minus bi. Minus z is minus a minus bi. So we can see that once again, z and z bar, they have opposite imaginary parts but same real parts. So in general, we can say that in a complex plane, the points z and z bar are just reflections of each other over the real axis. Right? And similarly, z bar and minus z, these are just reflections of each other over my imaginary axis. Right? So z bar and minus z are reflections of each other over the imaginary axis. But what about z and minus z? What is the relation between these 2 points? Well, from our previous example, we can see that minus z and z, these two complex numbers are exactly the same distance away from my origin, right? They're both the same distance away from my origin. And you can see that they're both in opposite directions from the origin. So what we can say is that z, this point z, if we were to rotate this 180 degrees anti-clockwise about the origin, we will just arrive at this point minus z, right? If we were to rotate z by 180 degrees, so minus z is just 180 degrees rotation of the point z about the origin, right? And my origin is just the real number 0, which is equal to 0 plus 0i, and that is this point here. This is my origin. Okay, so let's now take a look at another complex number. Let's say z is equal to 3 plus 4i, right? Now, what is the distance between this complex number and the origin? What is the distance between this complex number and the origin in my complex plane? So let's draw a complex plane, real axis and my imaginary axis, and plotting this point, we will have a point somewhere here. This is 3 plus 4i, which is equal to z, right? So the distance from the origin to this point will be just this, the length of this line, right? This is my origin. Now what can we do easily is just construct a right triangle like this, and if we were to just know this horizontal distance and this vertical distance, then we can just use the Pythagorean theorem to find this distance between these 2 points, right? And we can see that this will be just 3 units and this will be 4 units, right? So the distance will just be equal to square root of 3 squared plus 4 squared. And that is equal to 9 plus 16 root 25 is equal to 5. So this length is 5 units, right? So in general, if we were to consider a complex number a plus bi, and I wanted to find the distance between a plus bi and the origin, then I can just do so by using the Pythagorean theorem, where we will have square root of a squared plus b squared. This will be my distance. We're just squaring the real and imaginary parts under a square root. Now, whenever we're dealing with the distance between a real number, let's say we have x and this is a real number, whenever we try to find the distance between a real number and 0, we can represent that distance with the modulus of x, or the absolute value of x, right? Similarly, if I were to find the distance between a complex number and the origin, I can just use, so if I have a complex number z and this is equal to a plus bi, then to find the distance between this complex number and the origin, we can just represent it as the modulus of z, right? And that will be equal to square root of a squared plus b squared, right? And we can also call this modulus of z as the magnitude of my complex number z, right? This magnitude of z gives us the distance of my complex number from the origin, right? Now, before I move on, let's take a look at something. Let's take a look at something known as the distance formula. Let's say that we have a Cartesian plane like this. Let's say we have a point here. This is P1, which has coordinates x1 and y1. Let's say we have another point P2 with coordinates x2 and y2. If I were to find the distance between these 2 points, right, this distance between P1 and P2, then what can I do? I can just construct a right triangle like this and then apply the Pythagorean theorem. So if I just knew this vertical distance and this horizontal distance, I should be able to work this out. So what will be this vertical distance? That will be just the absolute value or the modulus of the difference between my y coordinates, right? So we will have y2 minus y1. We're considering the modulus because we want something non-negative, since this is a distance, right? And similarly for the horizontal distance, this will be x2 minus x1, right? So now applying Pythagorean theorem, we have the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared and this is actually my distance formula, right? We're not considering absolute value inside here because we already have a square term, so we will get something non-negative anyway. Keeping this in mind, we have shown how to find the magnitude of a complex number. Let's now try and evaluate the magnitude of some other complex numbers such as 5 minus 12i and 3 minus 3i. So we're trying to find the magnitude of these complex numbers. So starting off with 5 minus 12i, to find magnitude, this is just going to be square root of a squared plus b squared. Here a is 5, b is minus 12. We have 5 squared plus minus 12 squared. This is equal to 25 plus 144. So we have a square root of 169, and that is equal to 13, right? Similarly, the magnitude of 3 minus 3i, this will be equal to 3 squared plus minus 3 squared, which is square root of 18, that is equal to 3 square root of 2, right? So now suppose that we have some complex number w, which is equal to 3 minus 5i, and we have another complex number z, and that is equal to minus 2 plus 7i. And I want to find the magnitude of w minus z, right? So how can we do this? What we can first do is find w minus z. This is 3 minus 5i minus 2 plus 7i, right? So this will be equal to, so we have 3 minus 2, we get 5. We have minus 5 minus 7, we get minus 12i. So that is w minus z. So if we were to find the magnitude of w minus z, we are essentially finding the magnitude of 5 minus 12i, and this will be equal to square root of 5 squared plus minus 12 squared. We've already done this just a while ago in a previous problem, and that was equal to 13, right? So the magnitude of 5 minus 12i, this will be equal to 13. So now, if we were to plot these complex numbers on a complex plane, so let's plot these numbers on a complex plane. Right, so starting off with w, we have 3 minus 5i, that should be somewhere here, 3 minus 5i, and then we have minus 2 plus 7i, that should be somewhere here, minus 2 plus 7i. Now, if we were to try and find the distance between these 2 points, let's try and find the distance between these 2 points. So what we can do is we can just construct a right triangle like this. We can see that this will be 90 degrees. If I were to find this vertical and horizontal distance, well, this will be just the difference. So the horizontal distance will be just the difference between my real parts of these 2 complex numbers. So you have 3 minus 2, this is equal to 5, and the vertical distance will be the difference between my imaginary parts. We have minus 5 minus 7, that is equal to 12. So now if I were to apply the Pythagorean theorem, we have 12 squared plus 5 squared. Once again, this is equal to 100, square root of 169, and that gives us 13. So we have found that this distance between these 2 complex numbers is equal to 13, right? But as we can see that this is exactly equal to the magnitude of w minus z, right? So the magnitude of w minus z is equal to the distance between these 2 complex numbers, right? So let's say, suppose in general we have w is equal to a plus bi and z is equal to c plus di. So the distance between these 2 points in the complex plane is exactly the same as finding the distance between AB and CD in Cartesian plane, right? So if we were to find w minus z, we have a plus bi minus c plus di. This is just equal to a minus c plus b minus d I, right? So now if I were to find the magnitude of W minus Z, then you can just see that we will have the square of this term plus the square of my imaginary part, right? So we will have A minus T whole squared plus B minus T whole squared, right? And as you can see, this is exactly like the distance formula. So we can also apply the distance formula for the complex numbers, right? So if I were to find the magnitude of any two complex numbers, so if I were to find the magnitude of W minus Z, where W and Z are some arbitrary complex numbers, this will just be equal to square root of A minus C whole squared plus B minus D whole squared, and this is just equal to the distance between these two complex numbers.